Today is really the beginning of a brief conversation about organometallic reaction mechanisms. And to start that conversation, we're going to begin by thinking about how to count electrons and assign metal oxidation states. There are two popular methods for counting valence electrons associated with a transition metal, and we're just going to talk about one of them. This method is the closed shell or oxidation state method. And here you'll see an outline of what we're going to discuss. So why is this relevant? Well, metal oxidation states and valence electron populations give us mechanistic insight into transition metal-mediated reactions. You've already seen a large number of metal complexes in the context of oxidation reactions, and we're going to see a number more. So this conversation that we're having now should help us to understand the mechanisms of those reactions that much better. So if we want to count valence electrons, the first thing we need to do is, of course, draw the metal complex. And I've already taken care of that here with this rhodium complex. At this point, using the oxidation method, we want to draw the ligands in an ionic model, where they've been dissociated from the metal. What does that mean? It means basically taking the electrons in each bond and formally assigning them to the ligand they're associated with, like so. Be forewarned, these arrows do not indicate the motion of electrons in physical space. These arrows are used for the purposes of this formalism only. And what do they suggest? Well, they suggest that we're going to have a hydride depicted, a series of phosphines, and some carbon monoxide. Once we've done this, it's useful to assign each of these ligands as L-type and X-type ligands. So what do I mean by that? Neutral ligands are L-type ligands. So if you look at triphenylphosphine with these lone pairs, this is neutral, charged neutral. And so we can assign it pretty easily as an L-type ligand. And if we look at CO, there's an anion on carbon, but the whole molecule would be net neutral. So it would be an L-type ligand. By contrast, this hydride would be anionic, and so it would be an X-type ligand. Sometimes it's useful to make a little chart. As I've done here. Once we've done this, we're ready to assign charge to the metal. So the first step, if you want to assign the charge on a metal, is to incorporate the overall charge of the metal complex. This is funny to see here because this is an uncharged complex. If it were a charged metal complex, you would expect to see something like this, where the brackets have a positive or negative charge associated with them, and probably a counter anion or cation. Since there's no net charge on the complex, we don't actually need to adjust the charge on the metal. The second step then is to balance the net charge on dissociated ligands. Anionic ligands are X-type ligands, and we have one of those. So if this entire complex is net neutral in charge, then the rhodium needs to be positively charged to counterbalance the anionic charge on this hydride. So the rhodium needs to be in the +1 oxidation state. We've assigned the charge. At this point, we're ready to count the number of valence electrons on the metal. You add the number of electrons donated by the transition metal given its charge. So in this case, rhodium 0 is a D9 metal. Remember here that with transition metals, valence electrons occupy the d orbitals before they occupy the s and p orbitals in general. So if we know that rhodium 0 is a D9 complex based on the periodic table, then we also know that rhodium in the +1 oxidation state has 8 d electrons. And so as we're counting the electrons, we can say that it is contributing 8 valence electrons. Then we need to add the number of electrons donated by each ligand. Since we're using this formalism, we know we have 5 ligands, each of which donates 2 electrons. So 5 times 2 is 10, and that means that we have 18 valence electrons. Please note that for transition metals, the total number of valence electrons should generally not exceed 18, because you can populate the s, the p, and the d orbitals, and that gives you a maximum of 18 electrons. Okay, so let's try this one more time. I'm going to give you an example, and then you should pause the video and try to go through this whole process. Ready? Go. So hopefully the first thing you would have done is draw the ligands in their ionic mode and identify 4 L-type ligands. Next, you would have assigned the charge on the metal, identifying the net charge on this complex as positive, and therefore increasing the oxidation state of iridium to at least iridium 1. Since there's no net charge from the ligands, none of them are affecting the oxidation state of iridium in this formalism. Finally, you would have counted the number of valence electrons on the metal, identifying iridium in the +1 oxidation state as providing 8 valence electrons, and 4 ligands as providing an additional 8 electrons to give a total of 16 valence electrons. That's really all there is to it. If you want some more practice, go ahead and look back at some of the metals you've seen before, or just open up a paper and start to count the electrons and the oxidation state. Thanks for your time.